today we are going to be discussing degree of polarization. Before we get started, let's just quickly look at what we did in lecture number 9. So in lecture number 9, we were looking at the vectorial field. A vectorial electric field has two components. These are the polarization components. So the way a vectorial electric field is written is the following. So the E, the electric field, as the next component, and Y component. And then here we ask the question as to how the electric field vibrations in the two different directions, they are correlated. And the way to answer this question is through this kind of an interferometer. This is exactly same as our general methodology for an interferometer that we have discussed in time, space and angle, and we established that analogy. So here, unlike time space, we don't have to kind of split the field first, because the two components are already in two different directions, so we don't do that part. So we have these two different directions. Then we introduce a phase shift epsilon 1 and epsilon 2 in the two polarizations, and then finally we combine the field by looking at it at the output of a polarizer which is kept at an angle theta. So the coordinate axis at theta is this x prime, y prime, and this x and y, these are the original polarization direction. Now when we look at the intensity in this x prime direction, what we find that it has four terms. The first one is the component of this polarization x that passes through or makes through the polarizer x prime. The second term is the component of the y polarization that is able to pass through polarizer at x prime, and then the third and the fourth, these are the interference terms. Of course, if there is no correlation between x and y component, these two terms will be 0, and this we have expressed in terms of delta, which is the difference of epsilon 2 minus epsilon 1. And this jxy, which is this E star x EYT ensemble average, that is a correlation between the two field vibrations, that we can write in the following manner as we saw. And so this jxy, this we can write as under root jxx jyy. This is small gxy e to the I beta xy. This thing, the mod jxy, this is the degree of polarization coherence, and that's beta xy, that's the argument of G. Okay, so this way we see that the structure of polarization interference is pretty much the same as we have the structure for interference in time, space and angle. We can look at the visibility here, which is pretty much the same concept, and that is this intensity maximized over this delta, then the intensity minimized over this delta, so max minus min over max plus min, and this turns out to be this quantity 2 cosine theta sin theta under root jxx jyy, and this quantity. And we saw that this is pretty much the same structure if we recognize that this cosine theta is essentially k, the sine theta is essentially k2. Then we see that this structure is pretty much the same, or this structure is pretty much the same as we had for time, space and angle. There we didn't do cosine square theta or sine square theta, there we did k1 square, something that was fixed. So yeah, so this visibility, if we optimize the intensity, maximize or minimize it over delta, then this is the expression for intensity. So these concepts are pretty much analogous. These concepts in polarization are pretty much analogous to what we have in the case of time, space and angle. The one concept that we didn't discuss in much detail for polarization as we did for time, space and angle is the conjugate basis. So the question is, can polarization have conjugate basis? And the answer is yes. So if xy is one basis in which we are studying polarization, one can also look at polarization in this diagonal anti-diagonal basis, which is defined like that. So this diagonal anti-diagonal basis, that acts as a conjugate basis for polarization. Of course, we can have infinite number of conjugate bases for polarization, and all of those conjugate bases will be two-dimensional only. Okay, so this is what we did in lecture number 9. So today I'm planning to do the visibility of polarization interference in some more detail. So here is the polarization interference, here is the intensity that comes out of the polarizer, and that's the visibility that we have defined after optimizing over delta, and this visibility is equal to the degree of polarization coherence. Now, in this case, we now ask this question, what happens if we actually optimize the visibility over delta and theta? For example, that visibility if we define as this Wx prime maximized over delta and theta, minus Wx prime minimized over delta and theta, and this Wx prime max and min here, then this is also visibility. So, is there any physical interpretation to this visibility or to this quantity? Again, this is one thing that we didn't discuss in the case of time, space, and angle. There we had this k1 square and k2 square, which was kind of fixed for given interferometer. But here we are asking the question: if suppose for polarization interference, if we vary this quantity, this cosine square, this theta, which changes this and this as well, if we vary that quantity, and such that we look for the maximum of Wx prime as over delta and theta, then this way the visibility can also be defined. But if we do define the visibility this way, is there any physical importance to this quantity? Here this visibility equals the degree of polarization coherence, which is the correlation between the or degree of correlation between the field vibrations in these two different directions. So the question is there any physical importance of this quantity, this visibility? And that is the question we want to answer today. Okay, so in order to do that, let's substitute these relations. So for cosine square theta, we put 1 plus cosine theta by 2, sine square theta, we put 1 minus cosine theta by 2, and for jxy, we do jxx, jyy, the mod of jxy and e to the I beta xy. Let's substitute these quantities in here. So for cosine square theta, sine square theta, and jxy, let's substitute, and then we get this Wx prime is half jxx plus jyy. That's coming from jxx jyy, this 1 and 1, and then jxx minus jyy cosine theta, that's coming from this cosine 2 theta, cosine 2 theta, these terms, and then plus 2, we combine these two and then write it like twice jxx jyy sine 2 theta, mod of jxy and cosine delta plus beta xy. So that's the intensity. This is just the same expression, just written in just a different way. Instead of cosine square theta, sine square theta, we're writing it in terms of cosine 2 theta and sine 2 theta. Just a simple math. Now let's optimize it over delta. In fact, this we have already done it, but here I'm doing it in kind of detail. So if we optimize this expression over delta, then the maximum of Wx prime, the maximum is this quantity, which is simply that we put this cosine term as 1. So this jxx plus jyy, jxx minus jyy cosine theta plus twice this quantity, and that's what we have. It's just the k cosine delta plus xy is equal to 1, and that happens when delta plus beta xy is twice m pi, or delta is minus beta xy plus twice m pi. Simple. Similarly, we can also optimize it over delta such that it is minimum of Wx prime, and in that case this is the expression. Here we just put in the minus here. That means we have taken the cosine delta plus beta xy to be minus 1. That's when it is minimum, and that's the quantity we get. And the condition for this would be the delta equal to minus beta xy plus twice m plus 1 pi, and m is 0, 1, 2, the integer. So these are the expressions for the maximum of Wx prime and the minimum of Wx prime. Alright, so here is the intensity that comes out of the polarizer kept at an angle theta, and these are the maximum intensity that comes out when we optimize things over. This is the maximum minimum intensity that comes out when we optimize the intensity over delta. Fine. Now we want to do the optimization over theta. So for that we take the derivatives of this quantity. For example, we take the derivative of this one with respect to theta and first find the condition for the maximum of this quantities, and which will then give us the maximum over delta and theta. So we take this quantity, take the derivative with respect to theta, and find the condition for the maximum, and which will be this, that jxx minus jyy sine 2 theta. This simple one, this can be derived twice under root jxx jyy cosine 2 theta. This basically implies the sine 2 theta at the maximum. Sine 2 theta has to have this expression, that is twice under root jxy jyx divided by jxx minus jyy whole square plus 4 jxy jyx. This is just a condition that comes for the maximum, and cosine 2 theta has this expression. So that's the condition for the maximum of this quantity over theta. Okay, now substituting these for the sine 2 theta and cosine 2 theta in here, what we get is the Wx prime, that is the intensity coming out of the polarizer, the maximum of that, here it is maximum over delta and this is the maximum over delta and theta, so maximum of that will be when we put in these constraint over theta in this expression, and then we get that the maximum of Wx prime over delta and theta is this expression, half jxx plus jyy plus this quantity. This we simply can get by just substituting in for in here for cosine 2 theta and sine 2 theta. Okay, so this we can just simplify a little bit, and then this will have this expression. I mean, I definitely encourage all of you to kind of do the math and check that you do get this expression. It can be simplified further, and this will then become this. So the maximum of Wx prime over delta and theta is half jxx plus jyy under root jxx minus jyy whole square plus 4 jxy jyx. And again, this jxy is the quantity we are after. That's the correlation between the field vibrations in the two different directions. Okay, so that's the intensity expression, and this is the expression for the maximum of the intensity maximized over delta and theta. So that is the expression given in terms of jxx, jyy, jxy, jyx. Similarly, we can also do the minimization by optimizing over delta and theta, and for that we'll take the omega x prime expression that we had we take this minimum expression and then minimize it over theta. So if we do that, then the expression we get is Wx prime minimized over both delta and theta is this quantity. So this is the maximum over delta theta, and this is the minimum over delta and theta. Okay, so the visibility then which is optimized over delta and theta is this omega x prime maximized over delta theta minus omega x prime minimum, then omega x prime max plus omega x prime min, and this quantity comes out to be this twice jxx minus jyy square plus 4 jxy jyx divided by 2 jxx plus jyy. This we can then rewrite it in this form. This is square root, we have just opened it up, included this in here, so that there is a square and there is a 1 over 2 over there. This we can again rewrite jxx minus jyy square as jxx plus jyy square minus 4 jxx jyy, and this quantity then just remains here. And this then we can write as just 1 minus 4 jxx jyy minus jxy jyx jxx plus jyy square. So this is the algebra that we can actually do, and with this we are actually doing for some purpose which will be clear in a moment, but for now this is what we have. So that's going back again here, that is the intensity that one gets coming out of this polarizer kept at angle theta, and the visibility that is optimized over delta and theta has this expression, that is 1 minus 4 jxx jyy minus jxy jyx divided by jxx plus jyy whole square, the whole thing raised to the power half. Okay, so we actually want to simplify this expression little further and give it some physically intuitive meaning. But before we do that, let's go back as to how we represent a vectorial electric field. A vectorial electric field, we write like this, that E vector E as in terms of unit vectors x and y, these are the unit vectors in the x direction and y direction, and ext and eyt, these are the components of the field in the two direction. Now this vectorial way of writing the field we can also write as just as a row vector or a column vector as ex ey, and this ex is the strength of the field in the x direction, ey is the strength of the field in the y direction. So an electric field we can write it like this in the vectorial form, or we can also write it like this as a row vector. Okay, so this would be the field if this would be the representation for the field if the field was completely coherent, but in general fields are not completely coherent, they are partially coherent. At least in this course we have been discussing partial coherence. So things are only partially coherent, and in that case, as we have said, if the field is partially coherent, then this representation is only symbolic, and the actual representation is always in terms of the correlation function. So as far as correlation function is concerned, then we can write such a field as J as these four terms. So if the field is perfectly coherent, we can just write it as Ex, Ey, but if the field is not perfectly coherent, not fully coherent, then we have to write it in this manner. And what we are writing here, we are writing here the correlation of the field with itself, Ex star Ex, correlation of the field with itself in the other direction, Ey star Ey. That's like the intensity or spectral density in the x direction, spectral density in the y direction, and these cross terms are Ex star Ey, Ey star Ex. So this is just a way of representing a partially coherent field. We are writing it in this way for polarization because it is just 2 by 2 and we can write the whole thing. But when we did time space, we just looked at this Ex, E star X, Ey. That's the quantity we looked at. In fact, if we know this quantity Ex star Ey, then by putting in this, substituting for this X in here, we can get this quantity. By replacing Y here, we can get this quantity, and this is just a complex, this one is just a complex conjugate of this quantity. This correlation function Ex star Ey, that actually contains most of the information. Okay, so this is the representation of the field, which is in terms of a 2 by 2 matrix, and this represents the field which is partially coherent in the polarization basis. Here we are not talking about its temporal coherence or spatial coherence. Here we are only talking about is the its polarization coherence. So from the polarization coherence perspective, a field can just be written in terms of a 2 by 2 matrix. If it is fully coherent, then the field can just be written as a row vector. Okay, so now the terms within the matrix, these we can write as Jxx, that Ex star, I mean this we have already done, T Ext, Jxy, which is E star X, Ey, and so on. So that's the representation of the field in the polarization basis, the field that is not fully coherent. Okay, so this J is Jxx, Jxy, Jyx, Jyy. So the trace of J is Jxx plus Jyy, and the determinant of this J is Jxx, Jyy minus Jxy, Jyx. So that's the quantity. This is the determinant of J, and this is the trace of J. Now we go back to this expression for visibility. We realize this what we have in the denominator here is Jxx plus Jyy, and what we have in the numerator over here is Jxx, Jyy minus Jxy, Jyx, which is this quantity. So we can write the visibility as 1 minus 4 times the determinant divided by trace square raised to the half. So this is what we have. So the visibility of polarization interference, this visibility which is optimized over delta and theta, that is equal to 1 minus 4 times the determinant of J divided by trace of J whole square, whole thing raised to the power half. Now this is a basis independent visibility, as it doesn't depend on the choice of delta and theta. So we see this visibility, this is just dependent on the determinant of J and the trace of J, and we know the determinant of a matrix and trace of a matrix, these are basis independent quantity. No matter which way we rotate, it is the same. So this is something very intrinsic to the incoming field itself. It doesn't matter what phase we introduce between the two different polarization, where we keep the polarizer. It just doesn't depend on these quantities. So this visibility is something that is intrinsic to the incoming field, as it doesn't depend on delta and theta. Of course, for calculation of this visibility, we will need to change delta and theta and find the maximum of that quantity and so on. But once it is calculated, it has no functional dependence over delta and theta. Okay, so now that we have this visibility that is optimized over delta and theta, and this is the expression for that, let's look at what are the different cases of these extreme cases of this visibility. So first extreme case of visibility is when this visibility is equal to 0. So when this visibility is equal to 0, this means that this quantity is 0, the quantity inside this square root, which means that trace J square minus 4 determinant J, this quantity is 0. This then means that jxx plus jyy square minus 4jxx jyy minus gxy, this quantity is 0. If that is 0, then this plus jxx plus jyy square, we write that as jxx minus jyy square, and then the extra term gets cancelled from the term over here, this jxx jyy, and then we just have this. This then implies we can just rewrite this one. This is just jxx minus jyy square over here, but this jxy jyx, this term we can just write as jxy square, because jxy is this term and jyx is pretty much this, except that we have this minus over here, e to the minus I beta xy. So if you do jxy jyx, we are just multiplying this with its complex conjugate, and so we end up with jxy. So I mean essentially jyx is the complex conjugate of jxy, so the product is just jxy whole square. So this basically then says that this visibility 0 basically means this is the sum of two squares, and the sum of two squares can be 0 if and only if both the terms are 0. So if this term is 0, it means jxx is equal to jyy, and if this term is also equal to 0, this means that jxy, that mod, has to be equal to 0. So if the visibility, which is optimized over delta and theta, if you find that visibility to be 0, this means that the two polarizations have the equal weightage. That means the intensity that is associated with the, or spectral density associated with each polarization is equal there, and the degree of polarization coherence, that is 0. So either we state this or we state this, this is equivalent. So the visibility is 0, it means the two polarization have equal weightage and the degree of polarization coherence is 0. And also if we have that the two polarization have equal weightage and the degree of polarization coherence is 0, then we can be sure that the visibility, this optimized visibility, will be equal to 0. Now in this case, the form of the polarization matrix, which is jxx jy jxy jyx, this will take this form, that is 1 1 0 0. This we can see from here, because jxx jy has to be they have to be equal, so that's 1 and 1, and since jxy is equal to 0, hence this jyx will also be 0, and that's why these are two 0. So this is basically unit density matrix. So the form of the polarization matrix is pretty much of this unit matrix, and this we call the J unpolarized. This is an unpolarized light that has this kind of form. Let's look at the other extreme case, where the visibility is equal to 1. So if the visibility is equal to 1, this whole thing is equal to 1. If this whole thing is equal to, so visibility is 1, then this whole thing is equal to 1, and the only way that this can be 1 is when this term is 0. If this term can be 0 only when the determinant is 0. So visibility equal to 1 means the determinant of j is equal to 0, and this implies that jxx jyy jxx jyy minus jxy jyx, this quantity is equal to 0. This we can write as jxx jyy, and then now we are writing this jxy like this, jyx as the complex conjugate. If you multiply those, then we get this square root goes away, we have jxx jyy, and we have this this should be small jxy whole square, and then e to the I beta xy times e to the minus I beta xy, that gives us just 1. So determinant j equal to 0 means that we have this. This then implies that this jxy whole square, this quantity has to be equal to 1. So if this quantity is equal to 1, this basically means the degree of polarization coherence is equal to 1. So when visibility is equal to 1, the degree of polarization coherence is equal to 1. Now what is the form of the polarization matrix here? The form of the polarization matrix here is of this form, BC DD star, where BC minus DD, that is the determinant, BC minus DD star, that is equal to 0, and B has to be greater than 0 and C has to be greater than 0. So that's the condition we have. So BC DD star with BC minus DD star equal to 0 and B and C being greater than 0, that is a form of the polarization matrix we get when visibility is equal to 1, and we can call this one as J polarized. This is completely polarized light. Okay, so now that we have the expression for visibility, Now we ask the question as to what is the physical interpretation of this visibility that is optimized over delta and theta. Now to get to this question, we first need to look at this, that the general polarization density matrix can be uniquely written as this, that a general polarization matrix can be written as J polarized plus J unpolarized, and the form of J polarized and J unpolarized we just discussed in the last slide, that this is when the visibility is equal to 0, that's when we get this form of the polarization, and when the visibility is equal to 1, that's when we get this form of the polarization. This represents completely polarized light, this represents completely unpolarized light. And a generic polarization density matrix, an unknown state, can always be written as a state which is completely polarized plus a state which is completely unpolarized. That means if we had just this state, then the visibility will be equal to 1. If we had just this state, then the visibility will be equal to 0. And a generic state can be written as the sum of these two states. So what is J polarized? This is of the form BC DD star, and J unpolarized is just 1 0 0 1, and then we are multiplying it by this A, which decides the proportion of this unpolarized part versus the polarized part. And of course A, B, C, they have to be greater than 0, and BC minus DD star equal to 0. So that's how a generic density matrix can be written. So we have to let's prove this. Now in order to prove this, let's just realize that this Jxy, if we could write it this way, then Jxy is simply equal to B plus A, that is A plus B. This Jxx is equal to this B plus A. Jyy is equal to C plus A. And this Jxy is simply equal to D, Jy is simply equal to D star, because there is a 0 here. So this BC minus DD star, which we know is equal to 0. So BC minus DD star we can write like this, where B is Jxx minus A, C is Jyy minus A, that we are writing here, and DD star is Jxy Jyx. Of course this is equal to 0, because that's the form that we have assumed. Now this is a quadratic equation in A, so it will have two solutions for A, and if we solve it, we find that A, the first solution is trace of J plus trace of J whole square minus 4 determinant J by 2, and the second solution is trace of J minus trace of J whole square minus 4 determinant J. So these are the two solutions. Now for A equal to this second solution, we will find that the B, so I mean here this decomposition involves A, B, C and D, and now we have found here that this A satisfies a quadratic equation, hence it has two solutions. If we take just one solution, then the B corresponding to that solution, which we are calling B2, will take this form. This can be easily derived, and the point is that this is greater than or equal to 0. Now for this A2, this is the B2, and we can also show that the corresponding C2, that is also greater than 0. But if we take the first solution, A equal to A1, this one, in that case we can also derive the expression for B1 and C1, that's the corresponding B and C for this solution. But these B1 and C1 in this case will be less than or equal to 0. But what we need is that B and C, they have to be greater than 0. So what we find, that A equal to A1, that is the first solution, that is not an allowed solution, therefore this decomposition is unique. That means a general density matrix can be uniquely written as a matrix corresponding to completely polarized light, that means for which the visibility is 1, plus a density matrix corresponding to completely unpolarized, that is when the visibility is equal to 0. So this decomposition is unique. Okay, so now that we have that a general polarization density matrix can be written as a matrix corresponding to completely polarized plus a matrix corresponding to completely unpolarized, we just go back and look at the expression for visibility. This 1 minus 4 determinant J by trace J rho square raised to the power half. Just rewriting it as trace J square minus 4 determinant J, bring the square root, and this trace J instead of trace J rho square, because we have just put the square root here. This we can then write as Jxx plus Jyy whole square minus 4Jxy square by Jxx plus Jyy, simple math. This Jxx plus Jyy whole square, we can just open up and write it as Jxx minus Jyy square, and then this becomes plus 4Jxy square. This Jxx minus JYY, that simply is B minus C, because this is JXX is A plus B, JYY is A plus, JXX A plus B, JYY is A plus C. So JXX minus JYY is simply B minus C, and this 4JXY square, that is simply 4DT star, and JXX plus JYY is twice A plus B plus C. So that's what we get. This is for the visibility. This we can write as B, this B minus C whole square we can write as B plus C whole square minus 4BC plus 4BC. This is we writing the 4DD star, because BC minus DD star equal to 0. So that's why DD star we can just write BC, and so we see that this can be just B plus C, because this is B plus C whole square, so that's B plus C by 2A plus B plus C. So the visibility is B plus C by 2A plus B plus C. So this is with the understanding that we have written our J like this, that A plus B, A plus C DD star. Now what is B plus C? B plus C is the trace of this polarization matrix. So if we take the incoming field as having two parts, one is completely polarized, one is completely unpolarized, and this is the trace of the polarized part, and 2A plus B plus C, A plus B, 2A plus B plus C, that is the trace of this whole J. So visibility is the trace of the polarized part divided by the trace of the whole density matrix. Now what is trace of this density matrix? This trace basically represents how much intensity it represents. So this is the intensity of the polarized part of this field divided by the total intensity. So if we write a general density matrix, a general polarization matrix as a polarization matrix that is completely polarized and a polarization matrix that is completely unpolarized, then this visibility that is equal to the intensity of the polarized part divided by the total intensity. So that is the physical interpretation that comes out. We also give it a name that is called P, this is called the degree of polarization, and of course it is equal to this basis independent visibility. Now if this polarization matrix is normalized, so if trace J which is twice A plus B plus C, if that is equal to 1, then we get this P is equal to B by C, because twice A plus B by C, twice A plus B plus C, that is equal to 1. So P is simply equal to B plus C. So now this B plus C, that is equal to 1 minus this B plus C, that is equal to 1 minus twice A, which is what we write here. Then this is A equal to 1 minus P divided by 2. And so this J polarized plus J unpolarized we can then write as this BD star C, as we are dividing by P every time and is multiplying this P over here, plus this unit for A we are writing 1 minus P by 2. So 1 minus P and 2 goes inside, so half half. So this we just write as P J polarized with a unit trace plus 1 minus P J polarized as a unit trace. So this half plus half is 1, and B by P plus C by P, that is also equal to 1. So if we write the density polarization matrix in this form, that is as a unit trace polarized matrix, unit trace unpolarized matrix, then the degree of polarization is basically the weightage of this polarized part. That is the other interpretation we have of the degree of polarization. The first one is the intensity associated with the polarization divided by the total intensity, that is the degree of polarization. The other interpretation is that for normalized polarization matrix, if we write it in this manner, then the degree of polarization is basically equal to the weightage of the polarized part. So that is the visibility. So that is the physical interpretation associated with this visibility that we optimized over delta and theta. This is a basis independent quantity. It doesn't depend on the basis, so it has a lot of importance. We will get to see some of it, and very similar thing can also be done for time, space and angle, because we did not do this kind of optimization, this kind of visibility for time, space and angle, but it can actually, in principle it can be done, but those are quite involved, so we will not have time to do that in this course. Okay, so we will stop here. Thank you.